Okay, so good morning, everybody. Today we are going to continue the course of Malliavin calculus. Okay, so to begin with, let me remind what we have done during the previous session. So in the previous session, okay, I have introduced the Malliavin derivative operator. Okay, so let me remind the big points. Okay, so first of all, I have defined the set of elementary random variables, okay, that are just regular mappings of Wiener integrals, okay, and I have denoted this set by calligraphic S. And I remind that by regular, I mean that I want mappings of class C infinity with polynomial growths, okay, and in particular, S is a subset of L2 of omega. And I have said to you that what is nice with this subset is that S is dense, in particular in L2 of omega. Then I have proposed a definition for the derivative operator for this kind of random variable. And so when I have, okay, the expression star, okay, the derivative operator in the Malliavin sense, okay, is defined this way. So it's the sum of the partial derivative of small f at the corresponding Wiener integrals multiplied by hi of t, where hi is, okay, an element of L2 of 0 capital T that are the integrands, okay, in the Wiener integrals here. And in particular, if I apply this result to a basic Wiener integral, I obtain that dt of capital F is equal, in this case, to what I have inside the Wiener integral. Okay, so keep in mind that it is the kind of relation that I expect to have, okay, for what I want to do later on. Okay, so dt of f, the derivative operator, is something that depends on time and on w because I have inside Wiener integrals here. So I have a stochastic process, and I can prove that this stochastic process is in L2 of 0 capital T time omega, but it is not adapted in general, as you can see, okay, in the little example I have proposed during the previous one. Okay, so I have the derivative operator for elementary random variable that is defined this way. Okay, I have also interpreted this definition as a directional derivative. Okay, and we have obtained, okay, some nice relations. So first of all, that for elementary random variable, I have the classical formula for the derivative of a product, dt of fg, that is equal to g dt of f plus f dt of g. Okay, and that is the basis in order to obtain an integration by part later on. We have proved a duality result between elementary random variable, okay, and Wiener integral through the lemma 2. That is, the expectation of the scalar product between df and h in L2 is just equal to the expectation of f multiplied by the corresponding Wiener integral, okay, related to small h. And you see that here you have a duality relation in the sense that if you want to remove the derivative operator here, so remove from here to here, then you have to transform h into the corresponding Wiener integral, okay? And what is more, if I combine these two results, I obtain something that I can interpret as an integration by part formula, just applying, okay, this formula to a product, okay, and I obtain exactly this one. Okay, so this is the properties of the derivative operator for elementary random variable. A natural question is, it is possible to extend, okay, to more general random variable, the derivative operator? And the answer will be yes. And the key argument will be, in fact, this corollary one, okay, that will allow us to do this using approximating sequencing. So what are the situations at this point? Okay, I have defined the derivative operator on the set of elementary random variable. I know that this set of elementary random variable is dense in L2 of omega, and I try to extend the derivative operator using approximating sequences, okay? And the idea is the following, okay? So I consider f in L2 that may be approximated by density argument by a sequence in S, okay? I know that Fn converges toward F in L2 by the approximation, and I know from what I have said previously, that the derivative operator of Fn is well defined. And I said that it is that natural to say that if the sequence of the derivative is convergent in L2 of omega times 0 capital T, it should be interesting to define the derivative operator as the limit of the derivative operators. Okay. The problem is that, okay, if I do this, but I don't know if my definition is independent of the choice of an approximating sequence. And the answer is, in fact, yes, it is independent. And why it is independent? Because we have this result. This result that tell me that if I have a sequence in S converges towards 0, such that the derivative operator, the sequence of the derivative operators is convergent, then the limit of the derivative is necessarily equal to 0, implying that if I consider two sequences that converges toward the same variable in L2, if the sequence of the derivative is convergent, necessarily the limit of the two sequences of derivative will be the same. And so it is possible to extend, okay, the derivative operator using exactly this idea. So it's exactly what I do in this slide, and without ambiguity now, because I know that this definition, the definition of the derivative operator, okay, on the general domain calligraphic D, okay, is independent on the choice of an approximating sequence. And I can see something that is important by construction, because how I have, in fact, built this extension, but just adding in the domain of the derivative operator. So I start from elementary random variable. I consider, in fact, Cauchy sequences of random variable for this norm, the one that take into account, okay, the convergence in L2 for the random variable themselves and the convergence in L2 of omega times 0 capital T of the corresponding derivative. And in fact, I add in the domain, okay, all the limit corresponding to Cauchy sequences. And by construction, the domain equipped with this norm, okay, is complete. And we say that the derivative operator is a closed operator. So it is not continuous, okay, in the sense of what you know classically, but it is closed in the sense that if Fn converges toward F, and if D of Fn is convergent, necessarily the limit of D of Fn is equal to the limit Fn to D of F. Okay, it's what I mean by being complete for this norm. And what is more, okay, by construction, once again, the set of the elementary random variable that was already dense in L2 of omega is here, dense in the domain D for the norm that I have defined here. Okay. And finally, okay, I have some interesting property for this derivative operator. Okay, I have the chain rule. That is, if I have mappings here in the random variable in the domain, if I consider a mapping that is C1 and Lipschitz, then I have the chain rule formula, that is this one here. Okay. And what is more, okay, using the density argument, I can prove that if I restrict a little the hypothesis here, only supposing that phi is Lipschitz, then I can conclude that the domain is stable by Lipschitz mapping, okay, even if I don't have this formula, because phi here is no more supposed to be of class C1, okay. I have said that this proposition is that nice because it is the one that will allow us to say that solutions of stochastic differential equation at particular times, okay, are in the domain of the derivative operator with classical condition on the coefficients of the stochastic differential equation. You know that if you have a stochastic differential equation, the existence is ensured by, okay, Cauchy-Lipschitz type conditions. And what are these conditions? Okay, they are conditions mixing, okay, Lipschitz and sublinearity. Okay, and so since the domain is stable by Lipschitz, okay, we will be able to deduce that solutions of stochastic differential equations at particular points, okay, are inside the domain of the derivative operator, something that will be interesting for the financial part. Okay, I have also this behavior of the derivative operator with respect to the conditional expectation, meaning that if you have someone in the domain, if you consider the conditional expectations, they are still in the domain of the derivative operator. And I have this nice formula I can invert between the derivative and the conditional expectation up to this indicator function here. And I have deduced from this proposition a result that is important, saying that if I have someone in the domain that is fs measurable, dt of f is equal to 0 when t is strictly greater than s. So in some sense, it means that if you are fs measurable, it means that you depend on the Brownian trajectory up to time s. If you consider a derivative at a greater time, okay, the derivative is equal to 0 because t is strictly greater than s. Okay. And finally, I have said that, okay, we know that for elementary random variable, we have this nice formula for the derivative of a product. Okay, unfortunately, it's not possible to extend it, okay, in great generality to the domain D because, okay, if I do this, I have some integrability problems because, okay, I know that someone in L2 multiplied by someone in L2 is not something in L1, in L2, but only something in L2. So what you can have in mind is just to say that, okay, if I want to extend this relation, okay, it will be true if the integrability conditions are nice. And I have here this proposition that allow me to have two general conditions under which, okay, this formula is true for element in the domain if I add, okay, integrability conditions. And typically today we are going to use at the end of the today's session, okay, this statement A of proposition 4 prime, okay, saying that, okay, if I am in the domain here and if one is essentially bounded with the square of the norm of the derivative in L2 of 0 capital T that is also essentially bounded, then, okay, the conclusion holds. Okay. So it is what we have done during the previous session concerning the derivative operator. And today we are going to work with, okay, but in fact, something that we are going to define as the adjoint operator of the derivative operator in the sense of classical functional analysis. And this operator will be called the Skorohod integral. And we are going to see that this integral will be an extension of the Ito1 in some circumstances. Okay. So it's what we are going to do today. So I open my slides, okay. And before to start, okay, I will do some little reminder concerning Hilbert space theory and the definition of a joint operator. Okay, so we are going to consider, okay, H equipped with a norm defined this way, that is a separable Hilbert space. So it is, okay, the classical Hilbert space, okay, you work with, okay, for example, you have, okay, a space L2 equipped with the related L2 norm, okay, that is a separable Hilbert space, okay. Separable here is equivalent to say that I have a countable orthonormal family in this Hilbert space, okay. So I just want to remind, okay, an important result, that is the Ries representation theorem. And what is the meaning of the Ries representation theorem? It said that if you have a mapping A from H into R, okay, that is linear and continuous from H into R. But then, in fact, there exists a particular representation for this linear and continuous operator in the sense that there exists a unique vector in H such that for all x belonging to H, A of x is given by x0 x, where here I have the product, scalar product in H. Okay, So it means that all the linear and continuous form on a separable Hilbert space may be written as, okay, a partial, let's say, scalar product. Okay, so you can represent this one by a vector. Okay, so it's a result that you know, okay, that you have already seen, in particular in finite dimension. It's the one that allows to represent the differential of a regular mapping as, okay, using the gradient, okay, that is a particular vector, okay, representing, okay, the differential operator. So this is the risk representation theorem. That is true for any separable Hilbert space, okay? That is a representation theorem for linear and continuous form. Okay. From this risk representation theorem, we may define what we call the adjoint operator of A. Okay, so we are in a situation. So here we have A that is from H into H. Okay, not H into R, but H into R for H, and we suppose it to be linear and continuous from H into H. And I said that in this situation, there exists a unique A star belonging to linear and continuous from H into H, such that, okay, AX, Y is equal to X A star Y H for all X and Y belonging to H square. Okay, so it's what we call here A star is what we call the adjoint operator. Okay, so why I have this? So why A star exists? Okay, why A star exists? So for fixed Y, I can consider this mapping, the mapping from H into R that associate X, okay, A, X, Y. Okay? What can I say about this mapping here? But this one, it belongs to the linear and continuous mapping from H into R. From the fact that, okay, the scalar product is a bilinear form here, and from the fact that my operator A is a continuous one. Okay? So I am linear and continuous from H into R. So if I will use risk representation theorem, RRT, risk representation theorem. So from risk representation theorem, there exists a unique, okay, XY, I will call it because it will depend on Y, okay, such that, okay, such that what, okay, so if I denote this mapping here by phi, such that phi of X may be written as X, Y, X, H. Okay, and in fact, what I called A star of Y is by definition simply the little xy coming from the risk representation theorem, because this one here with this definition, it implies that phi of X is equal to A X Y. That is equal to what? A star Y X, that is X A star Y. So in a separable Hilbert space, I have the risk representation theorem that give me a general form for linear and continuous form on this separable Hilbert space. And using this risk representation theorem, I am able to define for any linear and continuous mapping from H into H, what we call the adjoint operator that fulfills, this condition, And for example, if H is equal to R to the power N, so you know that a linear mapping from Rn into Rn, may be represented by, a squared matrix of size n. And in this situation, if my operator is represented by the square matrix, then the adjoint operator is represented by what we call the transpose of the matrix. So something like this. So in our situation, we are going to have a look on, this kind of ID, not exactly this ID, but this kind of ID applied to the derivative operator, in order to define its adjoint operator that we will call the Skorohod integral, So here, what I want to do is to try to explore the links between the derivative operator in the Malliavin and the stochastic integral, having in mind that we have already obtained some kind of relation between them, in particular, by definition of the derivative operator on elementary random variables, I know that the derivative of a Wiener integral is equal to what I have inside the Wiener integral, that is, simply this thing. And what is more, I have this duality relation, we have already observed, that is the lemma 2 that I have proved, telling you that if in this expression you want from this one to remove the derivative operator, in order to remove the derivative operator, you are going to transform H into the corresponding Wiener integral, It's kind of duality relation in the sense that, you say that the scalar product between df and h in L2 of omega times 0 capital T, that is exactly this expression here, is just equal to what? To the scalar product between f and the stochastic integral in L2 of omega. So I have a kind of duality relation here. So now let's enter the definition of the Skorohod integral. So I denote by delta the adjoint operator of the derivative operator, that is an operator from the domain D into L2 of omega times 0 capital T. And delta is a linear operator, that is defined on a particular domain. So let's just remind that my derivative operator is something from D, and keep in mind that D is included in L2 of omega, with values in L2 of omega times 0 capital T. And the adjoint operator we are going to define here will be something, that will be in the other side. So it will be defined on the domain delta, that is included in L2 of omega times 0 capital T, with values in L2 of omega. So you see that, here you are from a subset of L2 of omega into L2 of omega times 0 capital T. Here you are from a subset of L2 omega times 0 capital T, with values in L2 of omega. So what is the domain of delta here? So the domain of delta is defined this way, and we are going to explain, this definition that is not that simple a priori. So I define as the domain of delta So the set of the element in L2 of omega times 0 capital T, for sure, okay? So it's the set of the U belongings to L2 of omega times 0 capital T, such that there exists a constant C belongings to R plus, such that for all F belongings to D, I want that this inequality hold. Okay, expectation of the scalar product between df. So df is well defined here because f is in the domain of the derivative operator. So here it's L2 of 0 capital T. I want that this quantity here is less than C times the norm of f in L2 of omega. So the domain of delta is defined this way. So it's exactly what I have written here. So U is in the domain of delta if there exists a constant such that, okay, for any f belongings to D, okay, this relation here is less than C times the norm of f, in the sense that you can control for f in D this expression, okay, by a constant multiplied by the norm of f in L2 of omega. And I say that when U belongs to the domain of delta, I define by delta of U the unique element of omega. Okay. Delta of U will be in L2 of omega, such that for any f belonging to the domain of the derivative operator, this quantity, that is the quantity I have inside here, is equal to the expectation of f delta U. In the sense that, okay, you see that you have a derivative operator here, you want to remove it, and then, okay, in order to remove from this one to this one the derivative operator, you have to transform U into by what I call delta of U, okay? That will be what I will call the Skorohod integral. Okay, so let's see a little, let's try to explain, okay, this. So keep in mind that this relation may be seen as the analogous of what we have seen here. We have this kind of relation here, but for not for U, a stochastic process, but simply for a mapping in L2 of 0 capital T. Okay, so you have this relation here that is the analogous of what I have in the definition of the Skorohod integral. Okay, but in some sense, okay, in the definition of the Skorohod integral, I extend what I have in the lemma 2 for stochastic processes instead of for mapping in L2 of 0 capital T. So you have here a kind of duality relation, and I will explain just after why I have this. Okay, so let me give you some explanation concerning this definition and some consequences. Okay, so suppose that you have U belongings to the domain of delta, okay? And let's define this mapping. I will define the mapping that associate for any f in D. So we consider this one, f. It associates this part here. That is the expectation of df U. It's something from D into R. And I will denote this mapping by phi here. Why not? Okay. So what can I say about this mapping? First, from the fact that the derivative operator is linear, I have phi that is linear. And plus, what I have the fact that phi of f is less than C, the norm of f in L2 of omega. Okay, why? Because I have this relation here. It's this inequality that gives me this one. Okay, so what I have my phi. Okay, that is D into R. F gives the expectation of dFU. Okay, in fact, phi is linear plus, I copy, the norm of F in L2 of omega. Okay, so I have a mapping here that is, in fact, phi is uniformly continuous because it is linear and fulfill this inequality, meaning that it is, in fact, I have something that is Lipschitz here using the linearity. Okay, why? Because if I take phi of f minus phi of f tilde, where f and f tilde are in D, from this one and from the linearity, I obtain that I am less than this one. So you have a mapping that is Lipschitz and so uniformly continuous. But what I know, moreover, is that I have the set of the elementary random variable that is included in the domain of the derivative operator, and I know that S is dense in L2 of omega. So D is dense in L2 of omega. So I have a mapping that is uniformly continuous when considered the norm here in L2 of omega. I have D that is dense, okay? I can extend. It's a classical result, okay? Phi can be extended from D into the whole L2 of omega. Okay, so I can consider phi from L2 of omega into R. Okay, so phi can be extended from D into whole L2 of omega, preserving the uniform continuity. And so what I have here now, phi can be considered as something from linear and continuous because uniformly continuous from L2 of omega into R. But by the Riesz representation theorem, there exists a Z belonging to L2 of omega such that for all, let's say, F belonging to L2 of omega, phi of F is equal to the scalar product between F and Z in L2 of omega. That is just here the expectation of Fz. And this is the scalar product on L2 of omega. But what I obtain, so this is true for any F belonging to L2 of omega. And if I consider F that belongs to D, I have the same expression, but for F belonging to D, phi of F is given by this expression because phi is just an extension of this one here. I have, in fact, the expectation of dFu here, L2 of 0 capital T, that is equal to this expression, expectation of Fz. So I repeat that if U belongs to the domain of delta, by definition of the domain of delta, this one fulfills this one. So I can extend it this way to obtain at the end, okay, this expression that may be represented as this expectation of the product between F and Z. And in fact, the Z I obtain here, Z is by definition delta of u. So if I come back to the definition I have written here, okay, the fact that such a delta u exists and is unique is a consequence of the Riesz representation theorem applied, okay, this way. Okay, so if you want, the domain of delta, that seems to be a little bit complicated here, is just, okay, the set of the u's such that I will be able to extend, okay, this mapping phi from D to L2 of omega, and then using the Riesz representation theorem on this separable Hilbert space, I can define, okay, simply delta of u as the unique element of L2 of omega that fulfill this relation here. So if I want to be a little bit simpler, so the domain of delta, I will copy it again, is defined as the set of the u belonging to L2 of omega times 0 capital T, such that there exists a C belonging to R plus for all F belonging to the expectation of the Fu is less than C times the norm of F in L2 of omega. This one this way, okay? And if you have understood what I have done, in fact, I can express exactly in the same way using, okay, the Riesz representation theorem, the domain of delta as the set of the u belonging to L2 of omega times 0 capital T, such that there exists z belonging to L2 of omega, such that the expectation of dfu and scalar product in L2 of 0 capital T here is equal to the expectation of f times z. And I have this. Okay, so maybe it's a simpler way to express the domain this way, but to prove that I have this equality from this one to this one, okay, it's very basic and just an application of the Cauchy-Schwarz inequality here, okay, just an application of the Cauchy-Schwarz inequality. And for the converse, to say that this one is included in this one, it's exactly the Riesz representation theorem argument I have used in the previous page of the course here, okay? And the Z I obtain here is what I called delta of u. So if I want to obtain delta of u will be the unique element fulfilling this relation here for any f belonging to, I have this, for all f belonging to D. Okay? So I repeat that to find delta of u, I start from this expression and I try to transform it, okay, as the expectation of f multiplied by someone, and if this someone is in L2 of omega, by unicity, okay, I will have, but that z is exactly what I call delta of u, okay? So this is my definition. So two things concerning this definition. First of all, I say the following. What is the expectation of delta of u? Have a look on this one. So here z is delta of u. Okay, so if I take in this expression here f equal to 1, I will have here the expectation of delta of u that is equal to what? But d of 1 is equal to 1. So I have this one. So delta of u is a centered random variable. Centered. This is the first important point. Second point, I said that in fact, delta is not a continuous operator, but it is an operator that is closed, okay, in the sense I have previously defined, okay, during the previous word. So what is this? I said the following. If you have a sequence UN in the domain of delta, such that UN converges toward U in L2 of omega times 0 capital T, and delta of UN is, let's say, Cauchy or convergence, because it is the same thing, okay, Cauchy in L2 of omega. I said the following. Then you have necessarily U that belongs to the domain of delta, and in order to compute delta of U is simply the limit of the delta of UN when n goes to plus infinity, the limit that is in L2 of omega. It's what I called, okay, I can summarize it saying that delta is a closed operator. And keep in mind that I have proved during the previous week that the derivative operator is also a closed operator. If I have a sequence Fn of element in D that converges toward F, and if D of Fn is Cauchy in L2 of omega times 0 capital T, I have defined D of F as the limit of the D of Fn. Okay, so it's exactly the same kind of thing. So just let me explain why I have this here. It's very basic because I will use this definition of the domain. So if I have UN that is in the domain of D, okay, what I have that for all F belonging to the domain of the derivative operator, when I want to compute the expectation of D of F UN, this is equal to what? By definition of the domain here, this is equal to the expectation of F delta of UN. Okay, by definition of the domain and by definition of delta of UN. But now I can pass to the limit simply. UN converges toward U in L2 of omega times 0 capital T, implying that this term here converges toward the expectation of the FU. I repeat, because UN converges toward U in L2 of omega times 0 capital T, I have expectation of the scalar product. So I need to have the convergence in this space. And here, delta UN is Cauchy. So delta UN is convergent in L2. And so here I can write here expectation of F limit delta of UN. And at the end, what can I deduce from this one? I can deduce that U belongs to the domain of delta because there exists such a Z here, Z that is given by the limit of delta of UN. And so delta of U is equal to the limit of the delta of UN. So this second point is very important because, the reasonings that we are going to do today, are of the same time of the ones we have done, during the previous session for the derivative operator. For the derivative operator, in order to prove some property, what we have done during the previous week, we have proved the property for elementary random variable. And then, using the closeness of the operator, we have tried to extend this property for more general random variable, in particular, the one in calligraphic D, the domain of the derivative operator. Here, it's exactly what we are going to do in the sense that D, delta, here, the derivative of the Skorohod integral is an operator taking as argument, stochastic processes. In fact, in the next slide, we are going to define what I will call some elementary stochastic processes that are related to this course. And the reasoning that we are going to do hereafter is that we are going to prove some property for delta for these elementary stochastic processes, and using the fact that the operator delta is closed, we are going to try to extend this property for more general element in the domain of delta. Okay, so exactly what I have done for the derivative operator that I will try to extend for delta using the closeness property of the operator. Okay, so first of all, let me define what is the set of elementary stochastic processes. Okay, so we are going to denote by S of L2 0 capital T, the set of elementary stochastic processes. What are they? There exist n belonging to n star. There exist n mappings in L2 of 0 capital T. There exist n elementary random variable, such that U is what is, in fact, let's say, a linear combination of product of element in S and element in L2 of 0 capital T. Okay? So U, an element in S of L2 0 capital T, is a sum of someone that is in S multiplied by someone that is in L2 of 0 capital T. And you obtain this way by multiplying these things, something that is in L2 of omega times 0 capital T, basically. Okay? And if I consider, well, if I consider this, okay? So keep in mind that for me, the set of the elementary random variables was the random variable of this form here, let's say, regular mappings depending on Wiener integrals. And from now on, the set of elementary stochastic processes will be the things of this form. Okay, I repeat, with this one in S, this one in L2 of 0 capital T. Okay, and what is nice here is that I have a very nice expression for delta of U in this situation. Okay, so this is the lemma 3. When I have an elementary stochastic process having this form here, delta of U is given by this expression. So an expression that seems to be complicated, but in fact that is not that much complicated. Okay, so let's do the proof of this relation and see what I have to prove, in fact. In fact, what I have to prove. So let's do the proof of lemma 3 here. So I start, I repeat, from U equal to this one. Okay. So what I want to prove, I want to find delta of U. Okay. Delta of U being uniquely defined by this. It's the only element that fulfills this relation. For all F belonging to D. So if I want to find delta of u, I have to prove that delta of u fulfills this relation for any f belonging to D. Okay? And I have to prove that if I plug inside this one, it works. Yeah. Okay? But just so I have this. We'll copy. So I have u that is equal to the sum from I equal to 1 to n of fi hi, okay, with fi belonging to s, hi belonging to L2 of 0 capital T. Okay, and I said that to find delta of u, I need to prove, I copy that expectation dfu is equal to the expectation of f delta of u for all f belonging to D. Okay. But just let's have a look on what I need to prove here. Okay, so if I prove that I have, starting from this one, that I have this one for a particular random variable in L2 of omega, I am sure that delta of u will be given by the expression I will find here for any f belonging to D. I say just, so this is the relation that I call relation star here. Okay. I will say the following. Star is true for all f belonging to D. In fact, if and only if star is true for all f belonging to the set of the elementary random variable. So why I have this? By simply because, so one side is obvious. If I have for all elements in the domain, since S is included in D, I have this side. For the other side, we are going to use a density argument because I know that S is dense in the domain D for the norm D I have previously defined. And so this side is obvious. I repeat, from the left to the right is obvious because S is included in D. If I have it for any f in S here, in fact, passing to the limit using this density argument, I can prove that I have it for any element in the domain. So in fact, to conclude and to prove, to find my delta of u, I have simply to do the job for f in calligraphic S using this density argument. Okay, so see the previous course for this density argument. Okay, so it's exactly what we are going to do. Okay, it's exactly what we are going to do. So I consider f belongings to S, and I will see what happened for the expectation of df of u. U being this element. Okay, so let's plug inside. It is the expectation of df sum fi of hi. And here the scalar product being a scalar product in L2 of 0 capital T. So it's the time t. Here I have something that depend on time t, I have something that depend on time t, and here I have random variables that doesn't depend on time t. So I can write this as the expectation of the sum of what? So I can remove I can use the linearity, okay, or the bilinearity of the scalar product, because this fi here doesn't depend on the time that is, okay, the variable of integration in the scalar product. So I can write the things this way. It's the sum of fi df of hi, and what's I can use here is the linearity of the expectation, and I can remove the expectation from the sum from the expectation. And I have this. Okay, so what I want to do now, the idea, as you see here, is that, okay, I want to remove the df here because I want to obtain such an expression. But keep in mind that what I have done during the previous session. During the previous session, I have proved the integration by part formula. This integration by part formula that we are going to apply now, okay? So you see that what I have, okay, in my proof is something of this form here, something of this form that I want to transform into, okay, making the d of j disappear. So we are going to use the corollary one, okay, in what I want to do. So, excuse me, we are here. So by corollary one, so I am here, equal, I continue here. By corollary one, what I have, okay, I can write this one as minus the sum of the expectation of f d of fi hi in L2 of 0 capital T plus the sum expectation of, okay, so I have this one here plus the sum, okay, of the expectation of fi integral between 0 and capital T hi of s dbs. At the end, what can I do? I can handle this relation here in order to say that what I have this term that is equal to the expectation of what? So I can put f into factor because I have f here and f here. Factor of what? Factor of minus the sum d f I hi in L2 of 0 capital T, it's the term coming from this one, plus the sum from I equal to 1 to n, okay, of what? Of the fi times the integral between 0 and capital T hi of s dbs. So if I summarize, I have this one that is equal to this one. And according to what I have said here, you have here simply delta of u. So delta of u is given by this expression here, expression that is exactly the one you have here, minus the sum of scalar product between d of fi and hi multiplied by the sum of fi times the Wiener integral. That is exactly what I have obtained here. So you have done the proof of the lemma 3, and you see that to find what is the value of delta of u for elementary stochastic processes, what I have done, I have simply used, okay, the corollary one that I have called the integration by part formula for the derivative operator. So I obtain basically the value of the Skorohod integral of an elementary stochastic process using the integration by part formula for elementary random variables and the derivative operator. Okay, so it's one of the property of the derivative operator on elementary random variable that allow me to deduce, okay, the property or the value of delta for elementary stochastic processes. Okay, so this is the lemma 3. So just a remark before to do this. So I will duplicate this one. Okay. I have the following. It's the corollary tree. So for the corollary tree, I take a particular U. So I take U of T, it's a stochastic process. That is what? It's the sum from I equal to 1 to N of Fi Hi, but I make so it's exactly the same form as the previous one, the one in the previous proposition. This one, it's an elementary stochastic process, if you want, in the sense of definition 5, but I want a particular elementary stochastic process. So we are going to suppose that Hi is in fact simply here an indicator function of someone that I call T1I, T2I. And for Fi, I suppose that Fi belongs to S and Fi is FTI1 measurable. Okay. So it's exactly what I take here. And for the Ti1, Ti2, okay, I just consider, okay, I start from 0 here with the T11. I have capital T with the Tn2, and you have, okay, the point in the subdivision here where, okay, for example, here I have Ti1, Ti2 here. Okay. So from this, I can say two things. I can say that for sure U belongs to S L2 of 0 capital T, because it's the sum of Fi Hi, where Fi is in S and H is in L2 of the 0 capital T. So I have an elementary stochastic process. And what is more, okay, from the course of stochastic calculus, you know that if you have a process this way, where you have here something that is FTI1 measurable, Ti1 being, okay, the Ti1 you have here is the lower point in the interval, okay? You can also say that, okay, you have U that belongs to, so L2 of omega times 0 capital T for sure, but that is also progressively measurable. Yeah, that is progressively measurable. So in this situation, okay, in this situation, I can apply the previous corollary, the lemma 3, because U is an elementary stochastic process, so I can use this formula for my particular U. Okay, so from lemma 3, so from lemma 3, I have what? So from lemma 3, I have the fact that delta of U may be expressed this way. Okay, so it's the sum from I equal to 1 to n of fi integral between 0 and capital T hi of s dbs minus the sum from I equal to 1 to n of what? Of the integral between 0 and capital T dt of fi hi of t here it's simply the scalar product between d of fi and hi in L2 of 0 capital T. Okay, so I just apply the lemma 3 for my very particular, excuse me, where I am here. So what I have this one. Okay, so for this one, why not? Okay, for this particular elementary stochastic process, that is in fact something that is progressively measurable because I impose this integrability condition and this measurability condition. Okay, so what I have here. So keep in mind that hi is equal to the indicator function of t, okay, I1, t, I2. Okay, so I have this. So delta of u is equal to what? Delta of u is equal to the sum from I equal to 1 to n of fi, and I multiply here by the Wiener integral, but Wiener integral of an indicator function, that is I obtain bti2 minus bti1 minus the sum from I equal to 1 to n of d fi hi in L2 of 0 capital T. Here I recognize, okay, from the expression of f and the measurability condition, what you have called in the first semester the integral between 0 and capital T of u of s dbs. And I want to see what happened for this expression. So what happened for the expression? So d fi hi is just what? Okay, it's the integral between 0 and capital T of dt of fi multiplied by the indicator function of ti1, ti2, t dt. Okay, so I have this. But what I obtain here, I obtain. So for the moment, okay, yes, I have used the fact that fi is fti1 measurable to say that here I have the stochastic integral of u. Okay, but I know also that from its corollary 2, I have that dt of fi is equal to 0 if t is strictly greater than what? So fi is fti1 measurable. So I have this one. This term is 0 if t is strictly greater than ti1. And in fact, it's exactly what I have here because t here belongs to this interval. So I can deduce that this is equal to 0. So this term is 0. To conclude, at the end, delta of u here is simply equal to the integral between 0 and capital T of US dBs in the case where my u is given by this expression. Okay, so for these very particular elementary stochastic processes, the one that have this form where Fi is an element of S intersected with L2 or FTI1, then delta of u is equal to this expression here that is simply equal to the integral between 0 and capital T of u of S dBs. Okay? So I see that for particular u, so for very particular elementary stochastic processes, then what I have called the Skorohod integral, okay, coincide with the classical Ito integral in this situation. Okay, so it coincides with this one. And I see that the argument is just, okay, a consequence of what I have proved previously, that is this value of delta of u for elementary stochastic process with this term that becomes 0 in the case where I impose some extra, let's say, measurability condition on the Fi. Okay, so I have this one. Okay, so for the moment, okay, so if I come back to the proof of the lemma tree, for the moment, everything comes from, okay, the integration by part formula for the derivative operator in the case of elementary random variable. So let's continue with the things. Okay, so what I have here. So now we are going to extend. So I have done the proof of corollary tree here. Okay, so it's the proof of corollary tree. Right here, proof of corollary tree. And now we are going to be interested in the proposition 5. So the proposition 5 tells us that, okay, in fact, the Skorohod integral and the Ito integral coincide for all the elements in L2 prog of omega times 0 capital T. Which means that in corollary 3, I prove this result for a very particular elementary stochastic process. And this proposition 5 tells me that I can extend, okay, in fact, to the whole L2 prog of omega times 0 capital T. Okay, so it's what we are going to do. So yes, I want to do this. So excuse me, I have this, okay. So now we are going to be interested in the proof of the proposition 5. So we can increase this. So we are going to do it in several steps. So of proposition 5. So we are going to do it in 3 steps. Step 1, I will take U as in corollary 3. That is U equal to the sum of Fi indicator function Ti1, Ti2, okay, where Fi belongs to S and Fi is FTI1 measurable. And for this step 1, I have already done the job. Okay, step 1 is okay. By corollary 3. because I have seen that in this situation, Skorohod and Ito coincide. So for this step, I have nothing to do because I have already done the job. That is a consequence of the previous result, okay? Step 2. Almost the same. But instead of having Fi in S and Fi FTI1 measurable, I suppose that Fi, okay, belongs to L2 of FTI1. So in some sense, I relax the condition on Fi. Here, I want Fi, okay, I want Fi to belong to the set of elementary random variable in the sense of this course, okay, and is FTI1 measurable. And here, I just suppose it to be, of course, FTI1 measurable also, okay, but simply in L2, okay, not in S necessarily, okay? So it's the step 2 we have to do. And so keep in mind that if I use the notation of what you have defined in the first semester with Bernard de Meyer, here you have U that belongs to epsilon of omega times 0 capital T. It's the set of the elementary stochastic processes in the sense of the semester 1 here that are the ones that are, okay, progressively measurable and piecewise constant, okay? So it's the set, okay, and on which you have defined first the Ito integral that you have then extended, okay, from epsilon to L2 prog. And my last step will be to suppose that U belongs to L2 prog of omega times 0 capital T. Okay, so I repeat, I want to prove that delta of U is equal to the Ito integral. First, I suppose that U has this form. And I know this from the corollary 3. I know that when U has this form, then delta of U is equal to the Ito integral. And what is this form? U is the sum of someone that is in S and FTI1 measurable and of this indicator function. And I know that this result is true. In the step 2, I relax, okay, the condition on Fi. Here, Fi is in S. Here, I suppose simply that Fi is in L2 and FTI1 measurable, okay? So I need to pass from step 1 to step 2, and then I will extend once I will have the result for all these elementary stochastic processes in the sense of the first semester's course, okay, of stochastic calculus with Bernard de Meyer. I will be able to extend, okay, what is delta of U for element in L2 prog, okay? And as usual, okay, in order to pass from step 1 that is known, okay, from corollary 3 to step 2 and to step 3, we are going to use density arguments. We are going to use density arguments. So I will write the things, what I have done here, excuse me. So I have this one. Okay, so I will just do the things this way. I have this. Okay. So keep in mind that the thing we are going to use deeply here to do the proof of proposition 5, and in fact to do the proof of the remaining proposition here, is that delta is closed. In the sense that if you have, okay, if you have un that converges toward U in L2 of omega times 0 capital T. And if delta of UN is Cauchy in L2 of omega, then U belongs to the domain of delta, and delta of U is equal to the limit of the delta of UN in L2 of omega. Okay? So for my step 2, I have a U that is equal to the sum from I equal to 1 to N of Fi indicator function T I1 T I2, where this one simply belongs to L2 of F Ti1. Okay, so the idea is to pass from step 1 to step 2. I know that I know the following. I know that S is dense in L2 of omega. It's something that I have said, okay, during the first slide of the previous course, that the set of the elementary random variable is dense in L2 of omega, okay? So I can deduce from this one, remind that L2 of omega is L2 of omega, okay, B, oh, F capital T here, in fact, okay, and mu, the linear measure. So I can deduce from the one that I say the following: S intersected with L2 of F Ti1, in fact, is dense in L2 of F Ti1. So I said the following: S is dense in L2 of omega. So it means that you can approximate of the random variables that are in L2 of omega by element in S. But in fact, if you have an element in L2 of omega that is FTI1 measurable, you can approximate it, okay, by elementary random variables that are FTI1 measurable, okay? In order to do this, okay, it's very basic, just take the conditional expectation. Okay, it's something that I have already said, okay, FTI1 here, okay? So the density of S in L2 of omega may be, or it's not even extended, it's just, okay, taking a particular case, okay, maybe expressed also as the fact that if I am in S and if I am FTI1 measurable, then I am dense in L2 of FTI1, okay? So the measurability condition is not a problem here, okay? So what we are going to do is, but in fact, to pass from step 1 to step 2, here I am simply in L2 of FTI1. So I am here. We are going to approximate the Fi by element here. So I can say the following: for any I belonging to 1 n, okay, there exists a sequence that I will call F I P, P belonging to n, belonging to S intersected with L2 FTI1, such that FIP converges toward Fi when P goes to plus infinity, the convergence being in L2 of omega. Okay, So we are going to approximate the Fi here by the Fip. Okay. So I repeat what I have. I have U that is equal to the sum of Fi indicator function of Ti1, Ti2. Okay. I have, so where Fi belongs to S intersected with L2 Fti1. I have defined for all I have defined Fi P, P belongs to N, such that, okay, so I am not in this situation here, excuse me. So U is this way, Fi simply in L2 of Fti1, okay? So I am in step 2. For all I Fip, okay, such that Fip belongs to S intersected with L2 Fti1 and Fip converges toward Fi when P goes to plus infinity, convergence in L2 of omega. Okay, so the idea will be to define a new stochastic process that I will define as UP. Okay, that is the same in this one where I have replaced Fi by its approximating sequence. Okay, so I have Fip indicator function Ti1, Ti2. So what can I say? I know that, okay, delta of UP is equal to this one. Because it's the step 1. I know also that, okay, since Fip converges to Fi in L2 of omega, I can prove basically that UP converges toward U when P goes to plus infinity in L2 of omega times 0 capital T. Okay, so I have this. Okay, but what I have from these two here? What I have from these two? I have UP that converges toward U in L2, and in fact in L2 prog, because I have processes that are progressively measurable. The UP are progressively measurable. U is progressively measurable using the integrability conditions on, or the measurability condition on Fi and Fip. So I have this one. But using these two and using the Ito isometry, if UP converges toward U in L2 of omega, okay, I have delta of UP that is equal to the Ito integral that converges when P goes to plus infinity toward by the Ito integral of U in L2 of omega. I have this. It's the Ito isometry that tell me this. But what I have UN that converges toward U in L2 of omega. I have delta of UP that converges toward this one when P goes to plus infinity. Since delta is a closed operator, I have U that belongs to the domain of delta and delta of u that is equal to the limit of the delta of up that is simply equal to this. So using this density argument, this approximation, and the fact that delta is a closed operator, then I have proved that if I have u of this form here, u of this form in the step 2 case, I can deduce from the step 1 that u belongs to the domain of delta and that delta of u is equal to the Ito integral. So I have done the job for the step 2. It remains to do the job for the step 1, and you will see that for the step 1, for the step 3. So step 3, it's u belonging to L2 prog of omega times 0 capital. And now we are going to use what we know from the first semester. From semester 1, there exists a sequence UN such that UN is as in step 2, that is, remind UN belongs to epsilon of omega times 0 capital T, such that UN converges toward U in L2 prog of omega times 0 capital T. Okay, it's because, okay, what I have defined as epsilon, okay, in the step 2 is exactly what you have defined as the set of elementary stochastic processes in the first semester. That is the set of stochastic processes that are progressively measurable, square integrable, and piecewise constant. Okay, the one where you have started to build the Ito integral, and you know that these processes are dense in L2 prog. Okay, epsilon is dense in L2 prog. It's the way that you have built the Ito integral. But I have a sequence UN as in step 2, such that UN converges toward U in L2 prog. I can say that by step 2, I know that delta of UN is equal to the integral between 0 and capital T of UN of S dbs, because I have proved that in this case, for UN in epsilon here, Ito and delta coincide. But what I have now, I will conclude exactly as I have concluded previously. UN that converges toward U in L2 prog. I have delta of UN that is equal to the Ito integral from the Ito isometry, delta of UN converges toward the integral between 0 and capital T of UF dbs. So I have UN that converges toward U in L2 prog. I have delta of UN that converges toward the integral between 0 and capital T of US dbs. The fact that you have 1 plus 2 plus the fact that delta is closed implies that U belongs to the domain of delta, and delta of U that is equal to the limit of the delta of UN that is equal to the integral between 0 and capital T US dbs. I have proved here that in the case where you have U in L2 prog, U belongs to the domain of the Skorohod integral. And in this case, Skorohod integral and Ito integral coincide. Okay, so you have an extension, okay, of the Ito integral that coincide, okay, with it, okay, for the elements in L2 prog. So in particular, this Skorohod integral is a way to integrate stochastic processes that are square integrable, but not necessarily progressively measurable. And I remind you that in the introduction of this course, I have said to you that, okay, I will define someone that will allow to extend the ITO without imposing progressively measurability. And what may be the interest in finance of such a tool? So it's not the topic we are going to be interested in this course, but to be able to integrate things that are not progressively measurable, okay, in the framework of mathematical finance may allow us, okay, to consider in financial markets, financial strategies that are not adapted to the filtration of the Brownian motion, okay, or not progressively measurable with respect to this filtration. That is, to consider financial strategy where I have more information than the one given by the market. And typically, okay, to consider such strategy allow us to be interested in what we call insider trading, okay, that is to take benefit of extra informations, okay, that you obtain out of the market, okay? But it's not what I will do in this course. In this course, I will focus on, okay, computation of Briggs. Okay, so the Skorohod integral coincide with the ITO1 for stochastic processes that are in L2 prog, okay? So it remains to prove two propositions, but I will do a little break and I will come back in a few minutes, okay? So see you in a few minutes. Okay, so we are going to conclude the today course by two rules of computations concerning the derivative operator in the Malliavin sense and its behavior with respect to Riemann and Ito integrals, okay, and a result concerning the Skorohod integral, okay. So let's have a look on this result here. Okay. So we are going to define something that I have used previously. So calligraphic D, okay, the set of the stochastic processes that are progressively measurable and square integrable, such that, okay, UT has this form. It's a form I have used previously. And here I impose for Fi, okay, to be in the domain of the derivative operator and, in fact, FTI1 measurable. So the FTI1 measurability of Fy ensure the fact that U is progressively measurable, okay, and I impose for Fi to be in the domain of the derivative, okay? So it's what I call calligraphic D. And then the proposition 6 tells us the following. So it seems to be a little bit abstract, but let's have a look on this result. We consider the closure of calligraphic D for this norm. Here it's a norm taking into account the convergence of stochastic processes in L2 of omega times 0 capital T, plus a convergence for the derivative operator related to a process U in D, okay? So it's a norm, okay? An L2 norm here, okay, taking into account the derivative operator. And I say that when U is in the closure of calligraphic D for this norm, then I have two results. One that is small b that tells us that you can invert between the derivative operator and the Riemann integral. So in fact, this is just a question of linearity, in fact, of the Riemann integral. And you have the small a that gives you a formula concerning what is the derivative operator of an Ito integral. Yeah. Okay. So let's have a look on this. So I will focus for the proof, okay, on this one. For this one, proof as an exercise that you can try to do at home. Okay. So I have this. Okay. So first of all, if I see this result here, I know that I have small a for u that is simply not a stochastic process, but just a square integrable mapping. Because we have seen together that in this case, the derivative of the Wiener integral, by definition of d, is simply given by ht. Okay, so in fact, this relation here is true. I don't have this extra term because in this case, dt of h is equal to 0. Okay, so small a is obviously true when u is a mapping and not a stochastic process, meaning that I have this formula for a Wiener integral with this term that is equal to 0. Okay, so it's the first remark I can do. For a Riemann integral, I have this. Okay. In the same way, where u is a mapping, okay, both terms are equal to 0 here, and I have this equality. So I want to prove this result for you in the closure of calligraphic D for this now. So I will do the proof of small a in 3 steps. Okay. So for D, I have elements in L2 prog that have this form, where Fi belongs to, okay, D. For the step 1, I will take you with this form. Where Fi, so is square integrable and FTI1 measurable. And I take Fi not belonging to D, but belonging to S. So in my step 1, I take Fi in S. The step 2 is for you belonging to calligraphic D. And what happened when I pass from step 1 to step 2? It means that I need to pass from an Fi in S to an Fi in D. So to an elementary random variable that is included in the domain of the derivative operator to the whole element in the domain, okay? And the step 3 will be u belongs to the closure of D for the norm D. Okay, so we are going, in fact, to do only the proof in the step 1 case, okay? And I just want to show you, okay, how to pass from step 1 to step 2 and how to pass from step 2 to step 3. And once again, we are going to use density arguments. We are going to use density arguments. So to pass from step 1 to step 2 here, we are going to use the fact that S is dense in the domain D for the norm D plus the fact that the derivative operator is closed. And in fact, you use this, that is, you will approximate, okay, an Fi in the domain D by a sequence that is in S, and then using approximations, okay, you will be able to pass to the limit and to obtain the result from the fact that the operator of derivation, D, is closed. The same all for step 1 to step 3, because since I consider here the closure of D for this norm, I will use the fact that D is dense in its closure for this norm plus the fact that D is closed. Okay, so we are going to use successive density argument in order to obtain the formula in its great generality. And in fact, okay, it's a reasoning that we have already done, because we are going to prove this formula in a basic, okay, case. And then we are going successively to try to be more and more general using density argument, okay, that will be able to handle because the derivative operator is closed, okay? So this is the idea of the proof of this proposition 6, okay? And why we consider this complicated norm? In fact, we consider this complicated norm because it's the one that will allow us to pass to the limit in the relation we are going to obtain. In fact, okay, so if you want to summarize, okay, this proposition and the statement of this proposition seems to be a little bit complicated, but as you are going to see in step 1, it will be very simple to prove the statement A of proposition 6, and then our objective will be just to be as general as possible using, okay, limits arguments. And in order to be able to pass to the limit and to use the closedness of the operator of derivation, okay, we need to work in the good spaces with the good properties of convergence, and it's exactly what we are going to do in practice, okay? So let's come back to this statement, okay, and we are going to do the proof of the statement A. So proof of proposition 6 small a for step 1. And by step 1, I means that I consider ut as, okay, or in order to cope with my notation here, we'll consider us, whatever, huh? It's just, I give another name to the variable. Sum from I equal to 1 to n, fi indicator function ti1, ti2 of s for fi belonging to s and fi fti1 measurable. Okay, so let's do the job. And I repeat that in order to pass from step 1 to step 2, you are going to consider that fi is no more in S but in D, as in the definition 3 here. And you are going to use the density of S in D for the norm D. Okay, so I will have my result for calligraphic D. And then to have the result from calligraphic D to its closure for this norm, okay, you are going to use the fact that the closure of D is dense in its closure for its norm, okay? So you are going to consider an approximating sequence and you are going to be able to pass to the limit using the closeness of the derivative operator. So in this step 1 here, okay, so let's prove this formula. It's the one that interests me here. So what is the integral between 0 and capital T of US dBs here? But simply, since I have a process that is piecewise constant, okay, by definition of the Ito integral, I have here simply fi BTI2 minus BTI1. And here I have by hypothesis something that is in S, and here I have also a Wiener integral, so I have something that is in S. And so when I want to compute dt of the integral between 0 and capital T of US dBs, by linearity, it's the sum from I equal to 1 to n of dt of my product of element in S. But I know from what I have done previously, so let's come back to what I have done during the previous week. Okay, I have in particular this slide here that tells me that if I have two elements in S, d of the product is equal to the classical formula for the derivative of a product. Okay, so let's come back to what I am interested in. Okay, so I am here. I can use this formula for this one here. So what is d? It is equal to, by two terms, the sum from I equal to 1 to n of dt of fi multiplied by, okay, bti2 minus bti1 plus the sum from I equal to 1 to n of fi multiplied by the derivative of this one. But here I have a Wiener integral, that is the integral between, okay, ti1 and ti2 of 1, okay, and I obtain as the derivative of this Brownian increment here, simply from the definition of the derivative operator for elementary random variables. And this is an elementary random variable because it is a Wiener integral. I obtain simply ti1, ti2, s. So I see that I have two terms and two terms that just come from the derivative of a product. What I obtain for this one, but you see that this one is the sum of fi multiplied by the indicator function. It's exactly us. So you obtain here the u, excuse me, it's a t here, it's not an s. So here, excuse me, I have just a t as a time variable here, and you obtain here simply u t. Okay, and what is this one? By this one, so dt fi multiplied by this one is simply the integral between 0 and capital T of dt of US dBs, because dt of US is equal to what? So US is equal to this one. Here I have an indicator function. Okay, so I have just a mapping. It's the sum from I equal to 1 to n of dt of fi, indicator function of ti1, ti2. Okay, so dt of US is equal to this one. Okay, so to summarize, I see that the formula that interests me, that is this one, in the case where I am in this very easy situation where my u is a piecewise constant, progressively measurable stochastic process such that fi is in S, then the formula is just consequence of the derivative of a product for elementary random variable, something that I have proved in the previous session. Okay, and now, since I have this in a very basic way for the step 1, I will be able to pass from step 1 to step 2 being element of calligraphic D, just using the fact that S is dense in D. And to have the proposition in its grid generality, I will just use the fact that if I am in the closure of D for this norm, I can be approximated by such elements, okay, with good convergence, and then I will be able to pass to the limit using the closeness of the derivative operator. Okay, so we have for the derivative operator, okay, nice computation rules, okay, with respect to Riemann or Wiener integral. Note in this case that since I work with something that is in L2 prog, here you have in this situation that the integral between 0 and capital T of US dBs here is just delta of U, because I have proved previously in the previous slide that Ito and Skorohod coincide in the case where I am in L2 prog. Okay, so this is the proposition 6, okay, something that we are going to use later on. So the derivative of an Ito integral is not U, but U plus an extra term that disappears in the case of a Wiener integral. But when I am a real stochastic process and not only a mapping, I have these stochastic integrals, okay, of the derivative operator at time t of my stochastic process. Okay. So let's conclude this session with this nice result that tell you the following. If you have an element U in the domain of delta, meaning that delta of U is well defined here, and if you have F in the domain of the derivative operator, if you suppose, so it's an hypothesis that F times U is in the domain of the Skorohod integral, then delta of Fu is equal to F delta U minus the integral between 0 and capital T of dTF ut dt. Okay, so I can write it as this one, F delta of U minus dF U in L2 of 0 capital T. Okay, so before to do the proof of this proposition, just have a look on what is this proposition. If F is constant, what is this proposition? D of Fu, I use my proposition that I suppose to be true. But in the case where F is a constant, this is equal to 0. So what I obtain simply is that when F is a constant, you have this, that is in fact a consequence of linearity. Okay, so I have this. So in the case where F is equal to a constant, so the proposition that I want to prove, the proposition 7, okay, is just a consequence of the linearity of delta. So it's in some sense something that extends the linearity to the case where F is no more a constant, but a random variable in the domain of the derivative operator. Okay, so it's my first remark. Second remark, suppose that you have the same hypothesis, but you suppose something that is a little bit more restrictive, that U belongs to L2 prog. L2 prog that I have proved to be included in the domain of delta. So if I apply my formula, okay, I have delta of Fu that is equal to F of delta U minus the scalar product between dF and U. But since I am in L2 prog, here I know from what I have proved previously that the Skorohod integral of U here is simply the Ito integral in this situation. And so here you have a result that allow you to transform the Skorohod integral of a random variable or of a stochastic process taking this form, f times u, okay, using here simply Ito integrals. So you pass in some sense from Skorohod to Ito. And why this is interesting? It is interesting because you know how to generate an Ito integral using a computer. Okay, I can approximate, okay, this one by a finite sum, and then, okay, just generate basically this with a computer, generating the trajectory of a Brownian motion. For the Skorohod integral, I don't have such approximation scheme, okay? But here you say that with this proposition, I will be able to pass from Skorohod to Ito, even if, okay, I have a u that is not progressively measurable. Okay, so you will see that in the financial application part, okay, then I will have such a trick in order to be able to compute efficiently the weights relative to my Greek's computation. Okay, so this is the two remarks I want to do on this result, and you will see that the second one will be used in the financial part. So to conclude, let's do the proof. If I want to prove this, okay, so proof of proposition 7. If I want to prove this relation, I have to prove that for all j belonging to the domain D, okay, I have to prove that the expectation of j time fu is equal to, okay, the expectation of the j fu in L2 of 0 capital T. Why I have this? But just because it's the definition of delta. Delta, excuse me, I have to prove that I have this delta of fu here. Okay, so if I want to find delta of fu, I have to start from this one and to prove that for any j belonging to D, then I have this relation. And the one I will find here will be exactly delta of fu. Okay, it's by definition of delta that I start from this one. If I put this one on the form of the expectation of j times something, this something is the Skorohod integral of f times u. Okay? So we are going to say the following. This is also true if I have this relation for all j belonging, so let's call it, so we are going to give it a name, okay, for this space, okay, we are going to call it, I have used calligraphic D, so maybe I can use A. With the same thing. Where calligraphic A is the set of the j belonging to D such that j belongs to L infinity of omega and the norm of dj in L2 of 0 capital T belongs to L infinity of omega. So it means that instead of doing the proof for any j in D, okay, I can restrict myself to this subset of D, okay, imposing some integrability condition on J and its derivative operator. So why I do this? Keep in mind that we have already seen this condition at the end of the previous session. So let's come back to the previous session. At the end of the previous session, I have said to you the following. If I want this kind of formula, that is the basic formula for the derivative of a product, I have basically this formula for elementary random variable. If I want to extend, okay, to more general situation, I need to impose some integrability conditions. In particular, I have this statement A that tell me that if F and J are in the domain, and if one of them fulfills this condition, that are exactly the condition I have written, okay, in my previous slide here, F is in L infinity of omega and dF L2 belongs to, is essentially bounded here, then the product is in the domain of the derivative operator, and I can apply the good formula for the derivative of a product. Okay, so here I am basically in the situation where I have considered by this good integrability condition, G in L infinity, and the norm of dj in L2 is also in L infinity. Okay, so why I have the right to do this? So why I have this equivalence here? I have this equivalence in green, okay, because by classical functional analysis argument, we can prove that A is dense in D for the norm D, implying that if I have this relation for any J in A, using the density of A in D for the norm of D, that is the one that take into account the convergence in L2 of the mapping and the convergence of the derivative in the good space, then I will be able, if I have only this one, to pass the limit in order to obtain this relation for any J in D. Okay? So I have this equivalence here, that is, in order to prove my result from the definition of delta, I have to prove this. And I just say that I can restrict myself to J in calligraphic A being defined this way, because this set is sufficiently big in the sense that it is dense in D for the norm of the operator. Okay? So we are going to admit the result in green, okay, because here, okay, it's not that complicated. And if I remind, okay, in one of the projects you will have, okay, you will have to prove this little lemma here in green. It's just, okay, using good approximations of J, okay, in order to be able to be in calligraphy. Okay, so let's do the job here now. And now it will be not very complicated to prove this and to prove that we have this formula, because we are going to be able to use the formula for the classical derivative of a product. Okay, so let's do the proof. So I am interested here in what? I am interested in, so for J belonging to calligraphic A, that is included in D, okay, and I know that it is sufficient to do the job for J in calligraphic A, I have to handle this. Okay, so I have this one. Okay, I have this. I know that f is independent of the time t because f is a random variable, so it depends on omega. So I can write this as f dj u in L2 of 0 capital T because f doesn't depend on t. But since j belongs to A and f belongs to D, I know that I have this D of the product fj is equal to f dj plus j df. Okay, so it's exactly why I work on calligraphic A, because when one of the two is in calligraphic A, I can use this formula. So if I continue this, I can replace f dj this way. I can replace it by expectation of d of f times j u minus, okay, the expectation of j df u. Okay, I have this one. What is this one? Here, once again, j doesn't depend on the time t, so I can remove it from the scalar product. So I can write it as this one, because I repeat, j doesn't depend on the scalar product, j independent of time. What is this one? By definition, of delta of u, this is equal to the expectation of f times j multiplied by delta of u. And if I summarize what I have in red, can be written as the expectation of what of j multiplied by f delta of u minus this part, that is dfu. If I summarize, I have expressed this one as this one, and it implies that the Skorohod integral of fu is equal to the term I have here, that is f delta of u minus df and u. That is exactly what I have here. Okay, so I have proved this formula, and once again, okay, if I have reduced in a good way my problem, that is, okay, when I remove all the problems of integrability and so on, this formula is simply a consequence of the formula for the derivative of a product. Okay? So I have proved the proposition 7, okay, that I will use in the financial part in order to be able to compute in a more efficient way the weights. Okay. So it closes the little chapter concerning the Skorohod integral. Okay, and in the next session, we are going to be able to start financial applications. Okay, so see you in the next session. Bye-bye.